Okay, we saw this table in the first video of this playlist, and I'm going to change the question yet again. First of all, what's the probability of one of these undergraduate students not being satisfied with their student government? We have not satisfied along this row. That's 78 out of the total of 374. So let me type that in, and we're going to get a decimal approximation to the 10,000ths place, i.e. 4 places after the decimal points. So let's see here. That's an equal sign. And 78 divided by 374. I'm getting 0.2085561,497. That would round to 0.2086. So what if we added in the condition that not satisfied, given that the undergraduate student is a junior? We would, instead of using the formula here, just to make this go quickly, given that the student is a junior, we would restrict the sample space. So we are looking at the 85 juniors here. And tell it not to fill that in. There we go. Up. Oh. I might not be able to do that. Give me just a moment to double check. No fill. There we go. And of that, we had the 11 that were not satisfied, given that they were a junior. That is right here. No filling. So we're looking at 11 out of 85. Which has a decimal rounded to 4 places. 11 out of 85. 0.1294117647. That's going to round down to 0.1294. By adding in that condition, the probability has gone down. And I don't want you to think that's what's always going to happen. If we were to draw a card and ask for the probability that it's a 10, you have 52 cards to start with. Oh, 4 out of 52, which as a decimal to 4 places. 4 divided by 52. 0.0769230.769. That's going to round down to 0.0769. Okay, so in the previous one, when we added in the condition that the student is a junior, the probability went down. If we add in on this one the condition that we've already drawn another card and did not replace it, we kept it, and it was a king. Now it's the probability of 10. That's 4 out of 51. You should see that's going to go up because we're dividing by something smaller. But in case that doesn't ring bells, 4 divided by 51 as a decimal, 0.078431375 is going to round down to 0.0784 by adding in the condition. This time, the conditional probability is higher than the probability itself without a condition. Can it ever stay the same? The answer is yes. Suppose you toss a quarter twice. So there's going to be a first throw and a second throw. And you're keeping track of what face. Either they're both heads, or the first is heads and the second is tails, or vice versa, or they're both tails. Now the probability of tails on a single throw is, of course, 1/2 if it's a fair coin. So probability of tails is 1/2. It doesn't really matter how I phrase the next part of this. Suppose I asked, what was the probability of tails given on the second, given that the first was tails? So second is a tail, given that the first was a tail. And again, just to make this go more quickly, rather than using the formula, I'm going to restrict the sample space to look at these two outcomes where the first was a tail. And of those, there are 2 of them. And one of them has the first one being a tail also. So that hasn't changed. So why is it going up sometimes? Why is it going down sometimes? Why did it stay the same here? Well, we're going to focus on the last part. This is our introduction to independent events. In words, 2 events, A and B, are independent if the occurrence of A or not has no influence on whether B happens or not. In terms of the conditional probability notation, that's written as P of A given B equals P of A, like what we saw with the coin toss example. And since this is about both events, P of B given A is equal to P of B. Now, I may differ from some instructors, but personally, I think that checking both of these is ridiculous, because we know that this is the probability of A intersect B over the probability of B. Since B came second here, it's going to be P of B in the denominator here. And on this one, the left-hand side, probability of B intersect A divided by the probability of A, because A came second here. Probability of A is in the denominator there. On either one of these, cross multiply to get rid of the fraction, and you're going to have, since the order of the intersection, A intersect B equals B intersect A, we come up with a much simpler way of checking with numbers whether 2 events are independent. Probability of the intersection equals the probability of, well, equals the product of the individual probabilities. And it goes both ways. If you have all 3 numbers, you multiply and it equals this number that you have, then you know A and B are independent events. All right, so what can we do with that?